Welcome to this explainer. I've always been absolutely obsessed with classic games, but I recently started digging into the raw mathematical reality behind how they actually work, and honestly, it completely blew my mind. Today, we're going to open up the developer's playbook together and figure out exactly how these digital worlds are constructed from the ground up. So, think about this for a second. What actually happens if you strip away the collision programming from a beautiful, fully rendered game world? You might kind of assume the world still exists, just, without you interacting with it. But the wild truth is, without that specific foundational code, these stunning digital landscapes are nothing but hollow, empty sets. They are basically digital paper mache. If a developer forgets to program collision detection, characters wouldn't just stand there like statues. They would literally fall right through the floor into a void of absolute nothingness. The gravity of the game engine would pull them right through the uncoded graphics. It's all just this massive, incredible illusion held together entirely by math. Section 1. Programming for easy tuning. To prevent characters from free-falling into that digital abyss, developers have to rely on some incredibly rigid structures, and this goes right down to the fundamental file names. Consider this brilliant little hack used in massive fighting games like Super Smash Bros. When you're managing thousands of unique animations, how you name a single file absolutely matters. Like if a developer names a side smash attack Sat Attack 4, putting the direction first, well, an alphabetical sort is going to scatter all the attacks across the massive database, purely based on their direction. Total chaos. But by using a logical sort, naming it Attack S4 instead, the base action, attack, gets grouped first. Suddenly, all your weak attacks, strong attacks, and smash attacks are perfectly grouped together. It sounds so ridiculously simple, right? But this is exactly the kind of trick that keeps the entire development team sane. And it turns out there's a really clever way they handle the actual math of a fight, using something called parameters. Think of a game's core structural code as a skeleton. It handles the raw logic of, say, a punch being thrown. But the muscles, how much damage that punch actually inflicts, are external numerical values known as parameters. By keeping these parameter numbers siloed in a separate spreadsheet, game planners can easily tweak the power of a punch from a 5 up to a 10. They don't have to bother the core programmers or, worse, risk completely breaking the structural code. The skeleton stays perfectly intact, while the muscles get pumped up or slimmed down right there in an Excel sheet. Section 2. Smart logic without cheating. Okay, so once the skeleton and muscles are built, developers need to breathe actual life into the computer-controlled opponents. But CPUs don't actually have eyes, right? They aren't looking at the gorgeous graphics like we are. Instead, they constantly read this invisible data table. They process zones, character states, and attack ranges to calculate their next move in mere milliseconds. Are you far away? Are you airborne? Does the CPU have a low hitbox range? If so, the invisible matrix tells it to just wait. But if you're close and grounded, boom, attack. The CPU is essentially reading the matrix of the game in pure data to flawlessly mimic a human decision. But here is the really fascinating catch. A computer reads data instantly. If a CPU uses that instant, entirely non-human reaction time to perfectly shield every single attack you throw, well, it completely ruins the fun. It feels exactly like the game is cheating, because in a way, it is. So developers intentionally handicap them. They program the AI to be aggressive, sure, but deliberately vulnerable to human tricks. They purposefully delay the CPU's reaction just a tiny bit so that you actually have a chance to outsmart it. They literally have to fake human imperfection just to keep the game enjoyable. Section 3. Graphical hacks and limits. Moving from the game's brain to its beauty, developers are constantly battling severe hardware processing limits. Just think about this for a second. How in the world did they render advanced dynamic particle explosions on the original Nintendo Entertainment System? How do you create massive scattered explosions on a retro console without completely crashing its incredibly limited memory? Because calculating real physics for that would literally freeze the console instantly. The answer? It's pure, brilliant smoke and mirrors. They used a hard-coded grid of 4-pixel sprite animations. Yup. The original Kirby game skipped complex physics entirely. Instead of generating true randomized particles, they used this genius hack of hard-coded coordinate patterns. They manually plotted tiny 4-pixel star sprites frame by painstaking frame to fake the visual of an explosion. It looked completely dynamic, but it was really just a preset flipbook animation playing out, saving an absolutely massive amount of memory. And hey, this isn't just some old school retro trick. Modern games still use intense optimization hacks constantly. Enter LOD, or level of detail. This is a super common optimization trick where 3D objects seamlessly swap out to lower polygon blockier models the further they are from the camera. Why do they do this? Because developers must ruthlessly prioritize processing power for the center of the screen right where the action is happening. You simply don't need a million polygons rendering on a tiny rock that's sitting 3 miles away in the background. Here's a perfect real-world example from a massive fighting game. In an Inkling-themed stage, there were these background tires that the art team had fully animated to spin, and it looked awesome. But spinning background tires waste precious processing power. Those spinning assets were flagged by the dev team, and their animations were heavily reduced. Why? Because they drained vital resources away from the main fighters. Every single ounce of processing power matters, and if a background tire is stealing frames from the main characters, well, the tire has to lose. Section 4. Blending clashing art styles. So, when you prioritize characters on screen like that, especially in crossover games, you hit another massive hurdle. How do you stop a bright cartoon hero and a hyper-realistic fighter from visually clashing? To keep them from looking like some messy, disconnected collage, artists meticulously apply 5 technical adjustments to every single character model. They desaturate the blindingly bright cartoon colors. They balance texture depths, meaning cartoon characters get more detail, and realistic characters actually get slightly less. They tweak natural body proportions. They refine small design details, like adding little scuffs or dirt. And finally, they use realistic physical reactions, making sure that even the cartoon characters have eyelids that blink naturally. This is exactly why a realistic, towering character like Bayonetta has her proportions slightly tweaked to actually fit the roster's scale, while a classic cartoon staple like Mario gets grounded in reality with high-fidelity, highly detailed denim textures painted right onto his overalls. It brilliantly bridges the gap. By pulling the cartoon characters toward realism and the realistic characters toward a more stylized look, they can both punch each other right in the face without ever breaking the visual immersion. And finally, Section 5. The player comes first. Look, all of these tricks we've talked about, the obsessive file names, the AI tables, the visual hacks, they are incredibly difficult to pull off. But when development inevitably gets tough, are you going to explain those technical problems to the player? No way! Because honestly, the player simply does not care how hard it was to code. They don't care about memory limits or frame rate budgets or team scheduling conflicts. They just care if the game feels good to play. All of those massive development hurdles have to disappear the very moment the game is booted up. So it all boils down to this incredible core philosophy. The final goal of creating a piece of work is nothing other than entertaining the player. If every single memory-saving trick, every math equation, and every graphical hack is ultimately just designed to create a fun experience, well, which of these clever development tricks will you sneak into your own digital worlds? Keep all of this in mind the next time you boot up a classic. Thanks for joining me on this explainer, and hey, keep playing.